Yeah, so the file size limitation has been 10 MB. Can't you uh, compress your video below 10 MB?
Okay, sir, I will try.
Yeah, uh, if you cannot do that, let me know. I will increase the file size. Actually, the problem is Google does not allow. I guess Google Drive does not allow beyond 1 GB upload on a single form. And since you guys are around 100 students, more than 100 students, so I have kept the limit of 10 MB for each of you.
Okay, sir.
So please try to bring the file size. And there are many online tools available. If you just type on Google how to compress a video, how to reduce size of a video, then you should get many results. Okay.
Okay, sir.
I hope you can see slides on your screens as well.
Yes, sir.
Yes, sir.
Yes, sir.
Yeah, yeah. Before beginning the discussion, I would also like to again sort of point it out that please also start thinking about your course projects, what you will be doing in this during the entire semester, and then maybe by the end of next week or beginning of next to next week, we have to finalize the projects for all of you. Okay. So just check out the feasibility of what you can do at your home and accordingly decide your projects. Okay, so let's uh, start our discussion. As all of you know that we have been talking about the story of electronics, how various electronics principles, the science of electronics was developed over uh, the course of history, and how the technology followed the science that was developed in 19th and 20th century. We had seen, so this is in summary what we saw, and we saw that it was in 1600s then when a first formal account was given for the electrical and magnetic forces, and it took almost 300 years when Maxwell gave equations for electromagnetic field, which essentially was a huge development in science. And after Maxwell's, or even before that, many inventions started. And as we know, electric bulb, DC motor, AC motor, induction, transmission lines, then telephone, radio technology, and those kind of technologies came about. And uh, we also saw how this story unfolded for electronics uh, engineering. Okay, so so then 20th century was basically the beginning of the electronics era in which the vacuum tube electronics came about. There are two vacuum tube technology, two kind of devices. One is diode, vacuum tube diode. One second is vacuum tube triode. Diode has a function of mainly rectification. Triode can do amplification as well. So triode in a way was more general device, and I also pointed it out that even during World War II, a computer a computer-like system was made out of diodes and triodes, switches and amplifiers, and that system was known as ENIAC, ENIAC, I guess that was the name of the system, and it involved many thousands of vacuum tubes. The problem was that it could solve many algorithms, it could compute many things, but the issue was that it was extremely challenging to find out the faulty uh, vacuum tube, and it took many days to set up an algorithm on the computer. So ultimately people realized after some time that the benefits that they were getting out of this computer were actually less than the amount of effort that was being put in its maintenance and its running. And that's also was the time when and even before that, I would say that the solid state technology was being explored in great detail, and many inventions followed around that time. So finally, during the World War times, technology saw huge jump, and particularly the electronic technology, because uh, a war of that scale, a war of second World War kind of scale, required many kind of automations, and that were done by the electronic equipments. For example, missile technology, even aircraft technology, all those kind of technologies saw huge jump during Second World War. Then came the transistor era. We had a brief discussion on transistor era, how it was discovered in Bell Lab in US. Uh, some people say that the transistor was discovered because everything about transistor, uh, or in principle, it was known, but how to fabricate a transistor was an accidental discovery, because this surface matching, fabricating a good surface, good junction was the main challenge uh, uh, in the fabrication of a transistor, and that was done uh, in 1947 by Bardeen, Breton, and Shockley. So that's what we essentially saw. And again, came a challenge that as time progressed, the amount or the task that we wanted to do with electronic equipments were getting more and more complex, which required more and more number of transistors to perform the task. And again, the problem was when we have multiple solid state transistors working in isolation with each other. When we have individually many solid state transistors, it was becoming extremely difficult to maintain the electronic system which had discrete electronic transistors, and that's why this idea of integrated circuits was being explored on very large scale, especially during 1950s, just after the discovery of a single transistor. And initially, there were many problems in making an IC, integrated circuit. One of the main problems was the isolation between the two adjacent transistors, actually. And that was also eventually solved independently by many people, I would say by many companies, electronic companies. And it was early 1960s when ICs could be made properly. And so after this IC invention, this just
Sir, you are on mute.
yeah, just hold on. Sorry, there was some important thing that came up. Um, so in early 1960s, this IC could be made, and the transistors, the isolation could also be done using junctions. And that's when all this started from 1970s up to uh, present times actually. So that's when the real progress in industry, electronics engineering actually happened. And this trend, which is also known as Moore's law, was given by none other than Gordon Moore, who was actually the co-founder of Intel. And Moore's law says, as we have also seen, that the number of transistors would double every 18 to 24 months. So every 2 years, the number of transistors on the same area of the chip will double. Uh,
Hello, sir.
so yes.
Sir, in the last slide, please explain
Sir,
the
please
second,
repeat this law.
sir, the
Sorry, can
second
you
point,
please?
last sentence, please tell again.
Second point.
On second line.
Okay, and somebody else also had a question or something.
Sir, I didn't understand this law. Repeat this.
Okay, so Moore's law is not a natural law, as I also told in the beginning. Okay, so Moore's law is a trend, I would say. It is a trend that the electronic industry was following, and it was a trend that was predicted uh, by Gordon Moore, who was actually the co-founder of Intel. Intel company was in the initial phase of its development in 1970s, late 1960s and early 1970s. And based on the trend of the number of transistors per unit area of the chip, Gordon Moore predicted that the number of transistors on the same area of the chip would double in every 2 years, approximately 2 years. So that means that in the same size of the same size of device, the number of transistors would be doubling every 2 years, which means that in a mobile phone, in every 2 years, the number of transistors would double, and that would increase their performance, their capability to do computation and other tasks. It is, however, as might seem from the name, it is not a natural law. It is not uh, a law of science. It is just a technological trend that was uh, given by Gordon Moore, and that the technological thing that was supporting Moore's law was scaling, basically. Scaling means the transistor size was getting scaled to low lengths of channel, low channel length, and that was essentially driving the Moore's law. So Moore's law also says that as the number of transistors per unit area of the chip is going down, the cost per transistor will go, so number of transistors per unit area of the chip is going up, the cost will go down gradually. Cost
Sir, can
per
you please
unit
explain
transistor.
why the cost goes down?
Yeah, so yes, I guess this point has come up again and again. For this, we need to understand where the most of the cost or most of the effort is uh, goes in semiconductor manufacturing industry actually, and most of the efforts or most of the investment that goes in semiconductor manufacturing industry is in the purification of silicon wafers, basically. So silicon is, as all of us know, silicon is a naturally found material. It is among the most abundant material in the nature, but it is like other materials. It is not. It is in impure form, and we cannot make devices in that form. So there are huge foundries, semiconductor foundries, where silicon is purified. Okay, so these establishing these foundries and then further making an ultra pure silicon wafer, that is a very costly process. And if we can make multiple transistors on the same chip, on the same silicon material, then the cost per transistor will definitely go down. The cost of the new device, the new mobile phone may not go down. So for example, few years ago, the mobile phones maybe had 1 billion transistor, but nowadays the same size mobile phone is having 2 or 3 billion transistors. But the cost is almost the same. The RAM has might have increased, the processing speed might have increased, but the cost is getting almost the same, which means that the cost per transistor is going down. Is this point sort of clear now?
So does it go down? The cost goes down per transistor because each transistor uses less amount of silicon.
Each transistor uses less amount of, yeah, definitely. So we need less silicon surface area to make transistors. So we need less number of wafers, less number of uh, purification steps. That's correct.
Thank you, sir.
Although it might seem that silicon is a very cheap material, even our sand has silica. Sand is silica. Sand is essentially one of the major components in sand is Si2O3, SiO2, many silicon oxides. But this purification step of silicon from SiO2 to Si, ultra pure silicon, that's a very that's now well established, but that's a very expensive process. And I also mentioned in one of the earlier classes that that is exactly the reason that most of the countries cannot establish silicon manufacturing capabilities, including India. So India being such a large country with such a large economy, even then, it is a huge challenge to establish a silicon foundry in India because the amount of investment, the kind of infrastructure that it needs, it is very huge. And if we can make uh, more number of transistors in the same ultra pure silicon material, that will essentially mean that the cost will go down per transistor. Okay. So so then this integration actually happened gradually. Integration means the development of integrated circuits, ICs, and initially in 1970s, around 100 components, 100 transistors could be made on a single 1 centimeter square of chip. That amounted to 10 logic gates. So one logic gate, for example, NOT gate, AND gate, OR gate, you might have read about these logic gates. That involves maybe roughly from 4, 5 to 10 transistors. And so in initial days, only 100 transistors could be put in 1 centimeter square of the chip, 1 centimeter square of the silicon wafer. And that time it was known as small scale integration. Gradually and very quickly, around 500 transistors, as the transistor size was going down, 500 and the integration technology, IC technology was being developed quite rapidly. Around 500 transistors could be made on the single chip, and that time it was known as medium scale integration technology. Then around uh, 100,000 to around 1 million transistors, when we could put that number of transistors on single chip, it was known as large scale integration. And then beyond few 100,000 or a million transistors, it is known as VLSI technology. And VLSI is quite famous. VLSI means very large scale integration. Essentially, it's a very simple term. The abbreviation is very simple. Very large scale integration means that now we are able to put around a million transistor on a small chip, essentially. Nowadays, yeah, the technology is even more advanced, and we can put even more than tens of millions or maybe a billion transistors, and that is sometimes known as ultra large scale integration, ULSI, or but VLSI name is most popular one, and which you might have also seen at many places in news uh, or at many places. But so this was essentially a brief introduction to the semiconductor industry and semiconductor uh, uh, devices in general. I would say it gave just a top level picture of things happening in this discipline in electronics and communication engineering. Now let's see in a bit more details what are semiconductor devices. Let's try to understand their science, basic principles at least. You will learn about these devices in more details in your upcoming courses. Uh, in this course, I will not go too much into the details of each device because that itself is a huge field. So we will just discuss the basic principles of semiconductors and the devices made out of the semiconductors. So before starting this topic, let me ask you a question. What is a semiconductor material, in your opinion?
Conductivity intermediate
Conductivity
between metal and
between
insulators.
insulator and conductor.
Intermediate conductivity.
Highly
Yes, that is also apparent from the name of the name semiconductor. And you are right about it. It is the conductivity of semiconductors is in between metals and insulators. And that is the conductivity
Intermediate
of
forbidden
electron.
energy gap.
Intermediate forbidden energy gap. That's also right. What is the forbidden energy gap, by the way?
The energy level
Electrovolt.
difference between the
Energy
valence
difference between valence band
level
and
and
conductors.
the conduction band.
Energy level difference between, sorry? The
Valence
Valence
band and
band
Valence
conduction
band
band.
Valence
and
band
conduction
and
band.
band.
Okay, and what are valence and conduction bands?
Energy levels
The
where
valence band,
conduction
the
is possible
electrons
is
cannot
conduction
float
band,
in the valence
and energy
conduction band.
levels where valence electrons reside is valence band.
Sorry, can you repeat because two of you were speaking, so I could not hear properly. Can you please repeat what you just said?
So the energy levels where electrons who participate in conduction reside is called conduction band, and energy levels where electrons in valence band are there is called valence band.
Yeah, anybody else? Yeah, you are partially right. Anybody else would like to add?
So we can control the conductivity of semiconductors manually by a large amount with doping and all.
Yes, exactly. Yeah, that's another point. Yes. Yeah, so there are many concepts in semiconductor material, semiconductor devices. One is, as you mentioned, the notion of bands, conduction band, valence band, the band gap, conductivity, manipulation of conductivity, doping, and mobility. But do you guys know why the bands are formed in solids or maybe in semiconductors?
Because there are many atoms uh, close to
Okay.
each other.
Okay, so that then what?
Electron of one atom
Then
impact
electrostatic
nucleus of other.
interaction occurs between the atoms, and so the energy levels form energy bands.
Why the electrostatic interaction uh, results in energy bands, by the way?
So may I explain?
Yes, please.
So because there are so many atoms in a close vicinity, the loosely held electrons can move in the in all the atoms field. So that's why they are called semiconductors.
They are called, sorry,
Uh,
semiconductor.
that's why the bands are formed.
Yeah, but that does not explain why the bands are formed. If the electrons can move in uh, or close to many atoms,
Sir,
how
sir,
does that imply
each
that?
sir,
So
each
because they
atom's
are
electron can move in the vicinity of other atoms. That's why.
so we
Yeah,
can
so
say
that's why.
concept of energy comes when there are fields around that electron or atom, and as there are fields, there are energy levels.
So
Fields, sorry, what do you imply by
So
fields here?
electric fields.
And electric fields of what?
Sir, sir, what, sir?
No, electric fields of what? So there are, you said that
Sir, like
there are
protons,
electric,
electrons of other atoms.
yes. So yeah, now please complete your or your point.
Sir, I want to say like there are many atoms as you are saying, and those atoms have proton electrons. So there are fields in which electrons are in between. Like so, those fields are causing the concept of energy here.
Those fields are causing the concept of energy.
Yes, sir. They are giving rise to this energy concept.
So what is the energy concept? We are talking about bands and band gaps.
different electrons
Are you
have
talking
different energy. So this made a range of energies.
range of energies?
Uh,
Yes.
Range of energy which is called band energy, bandwidth.
Okay.
So various
Uh,
energies
uh,
are so close to each other that they form a band.
Various energy levels are so close to each other that they form the band. Okay. But why band gaps?
Different electrons are interacted differently, so their energy will be different.
Yes. No, you guys know quite a bit of about the semiconductors, and actually, that's how it is written in most of the introductory texts on semiconductors. The way you explained it, that is how it is written in most of the books. But actually, it cannot be properly understood without quantum mechanics because we are talking about the energy bands of electrons, and electrons are inherently quantum mechanical particles. Electron-electron interactions, electron nucleus interactions, all those interactions are accounted by the Schrodinger equation. And once we solve the Schrodinger equation for electrons in the solid, then we naturally see, even from the maths, that there is a certain range of energy values for which electron wave function exists, and there is a range of energy values for which the electron wave function is not at all allowed. And that is essentially where this idea of uh, bands and band gaps come about. But whatever you said is right from a heuristic or from a qualitative point of view, and that's how it is written in most of the basic standard textbooks of uh, semiconductor devices. But I would just like to point out that this explanation is insufficient uh, in explaining the bands and band gaps of semiconductor material.
Sir,
Even though
so
even yeah
sir,
yeah
what you're trying to say is that the radial nodes that occur in any of the orbitals, those are actually the energy gaps that are mentioned.
no again orbitals are generally we have atomic orbitals and molecular orbitals. Those are also uh, I would say nanoscale concepts. But solids are huge. Solids are pretty big in size. There can be many Avogadro number of atoms in solids, even in small solids. And when we have such a large number of atoms, then it is no longer possible to talk about orbitals. Uh, However, I would say from a fundamental science point of view, as there are nodes in orbitals, there are band gaps in solids. Yeah, from fundamental science point of view, that is right. But it cannot
Can we
be
say,
just, sorry?
so can we say that in the band gaps, the chi-square value is 0?
Exactly. Even psi value is 0 in the band gaps. So that's why the electron wave function does not exist, or is not physically and mathematically feasible for those energy values. So there are certain energy values for which there is no solution of electronic Schrodinger equations. And that's why we have to take psi and psi square to be 0 in the for those energy values, and that's where the band gaps actually come about. Yeah, so that's a bit, I would say, advanced, and uh, this will be discussed in more details in one of your electives that will be there uh, in your maybe third year, I guess. Yes, and in one of the courses in your second year, ECN242 course, which is about electronic devices. So we will have a brief review of what is semiconductor, uh, what is electrons in semiconductor materials, and I guess most of you guys know about it. But ultimately, as we saw, that it is all about electrons. It is all about trying to control electrons and electron flow. And but if we classically, if we have a classical analog of electron, if we try to model electron classically, electron is roughly uh, a particle of around 1 femtometer of radius. Although that is not really true, electron is a quantum mechanical particle, and we cannot say, or nobody can say, that electron has a radius. Electron does not have a radius. It has a wave function, and wave function can spread out. But generally, if the electron is confined in an atom, in an orbital, it can be roughly compared to a classical particle of 1 femtometer of size. So that's, you can imagine, that's an extremely small entity. Uh, the size of one atom is around of the order of 1 angstrom, 1 to few angstroms, and 10 to the power minus 10, 10 to the power minus 15 is the electron. So even inside the atom, electron is almost invisible. It is uh,
Sir, your
0.001%
Sir,
of. Yes,
sir, your
your screen
screen
is
is
not
not
visible.
visible now.
screen is not visible.
Yes, sir. Someone
Sir,
else
someone
is
has
sharing the
started
screen.
start.
Okay, okay. Yeah, it was started by the students, or one of the students, or
Sir, I think it's Nikita's screen.
Yes, sir.
I guess it should be visible now.
Yes, sir.
Please
Yes,
confirm.
sir.
Yes,
Yeah,
sir.
yeah. So,
Yes.
so these things, these are just general details. And as I said, electron, even in an atom, electron is a very
Sir,
small.
I am not able to see
Sir,
your
Uh,
screen.
again,
Sir,
there is.
again it
Screen
shows.
is not visible to us.
uh,
Sir, it is
okay,
again whiteboard screen.
it is again. Okay, I think it should not happen that way. Maybe from I'll see that the students cannot do these things because otherwise one of you, any one of you could do this. Is it better now?
Yes, sir.
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 Yeah. So yes. So this is what it is, and as you also know that we are always concerned about the conductivity in electronics and electrical engineering, and the conductivity of metals is quite uh, significant. It is typically of this order or even more, around this or 10 to the power minus 10 to the power plus 7. Conductivity of insulators is extremely small, 10 to the power minus 10, and conductivity of semiconductors is highly tunable, so to say. It can range anywhere from 10 to the power minus 6 to 10 to the power 4. Basically, anywhere between a mild insulator to a mild conductor. Okay, and that is this property or this attribute of semiconductors. It make it sort of because of this attribute, those are semiconductors are the materials which are used in electronics engineering. Because in electronics engineering, we always want to control the flow of electrons, and that is possible mostly in semiconductors. Semiconductors are the most versatile in that sense. Okay, and uh, so with time, semiconductor industry has also evolved quite a lot, and so there are three important semiconductor materials. Silicon, everybody knows. Silicon is the material out of which most of the devices are made of. But silicon is not the material that was there since beginning. In the beginning, it was germanium that was used to make electronic devices because fabrication of silicon was not possible. It was extremely difficult to purify silicon and make devices. And if the silicon is not pure, then we cannot make any device out of it. The conductivity, the carrier concentration, everything is very bad in impure silicon. So that's why germanium was there. But the problem with germanium was that its conductivity is highly dependent on the temperature. So as the ambient temperature used to change, the conductivity of germanium used to change as well. And that's why the device reliability or the device functionality was not very stable. Okay, and that's why very soon uh, people started finding an alternative to germanium, and silicon turned out to be the among the best alternative. And there were many reasons. One is silicon is among the, as I said, silicon is among the most abundant materials in the nature. So there is no uh, supply shortage. There won't be any supply shortage of silicon, so to say. Uh, Silicon has very good temperature stability. The conductivity of silicon is extremely stable with respect to temperature. So the second problem is also resolved, which was there in germanium. The only problem is that silicon is extremely difficult to make. Silicon needs very high investment, billions of dollars actually, to make a good foundry, to make a good transistor. So that is the only shortcoming. But with time, what happened was big industries started setting up silicon foundries, and now the silicon foundries are in mature stage at many places in many industries and many countries. And now even if somebody wants to uh, replace silicon, it is no longer possible. Or, I won't say it is no longer possible, but it is extremely difficult. It has a huge inertia because billions of dollars or maybe trillions of dollars of funding is there in silicon foundries. So if you want to, if maybe tomorrow you come up with a new material and you say that let's now make transistors out of this new material because this new material has better transistors, better reliability, more speed. Even then, So even if the science is indicating that this new material is better, even then practically it is extremely unlikely that silicon will be replaced anytime soon. Maybe in long run it might happen gradually. Uh, uh, Things might change, but silicon now has a huge inertia. The third important semiconductor material is gallium arsenide, which is a composite material. Composite means it is made out of two elements, gallium and arsenic, and the important property of gallium arsenide is that it can uh, be used in high frequency applications. When we use high frequency application, silicon does not perform very well there because the number of electrons in silicon is less, or I would say medium. More, the mobility is also not uh, so great that it can be used in high frequency applications. Gallium arsenide in that sense, or nowadays gallium nitride is a better choice. So nowadays, most of the devices are made out of silicon material. High frequency devices are made out of gallium arsenide or gallium nitride. Germanium is also used in some applications where we need high mobility, but its presence has sort of gone down in electronic devices. And on this slide, I also have the molecular configuration or electronic configuration of these elements, silicon, germanium, gallium, and arsenic. And as you can see, there are in silicon and germanium, there are 4 electrons in the outermost shell. In gallium, there are 3. In arsenic, there are 5. So, so let me ask you one question here, and that is not about electronics. Why, why is why do we have discrete energy levels here? So in atoms, as you can see in these diagrams as well, we have discrete energy levels. So we have, uh, or maybe we have orbitals with different energies, but these energy levels are fixed. So
Sir,
there is
because of,
these energies are not continuous. Yes.
sir, because of conservation of quantization of angular momentum.
Because of the conservation of, sorry,
Because sir, energy is quantized. It comes in packets, not as a continuous beam.
okay.
Sir,
So
Bohr
what does
theory.
that mean? Yeah, it is. Yeah, you're just talking about a theory or a statement. Can you please explain in bit more detail so that things are clear?
Sir,
What
I'm
element
afraid
or
I
what?
don't have that good an understanding of it.
Yeah, Dekshant, you want to say something? You mentioned about Bohr's theory. What principle of Bohr's theory says that?
Sir, the same like that energy is quantized, and about angular momentum, that energy and angular momentum are linear, integral multiples of some basic unit. And
No, but
sir, we are using
what is?
that, sir. That electrons are like in accelerated motion, and uh, as they are not approaching nucleus, so their energy is like constant. Otherwise, they will fold to nucleus uh, like that, sir.
No, so you said that energy is quantized. What is the quanta of energy and how is that relevant here? So many of you, I guess, mentioned that, but how is that relevant here?
Sir, only those orbits can exist in which the angular momentum is an integral multiple of h cross.
Okay. Mhm.
So
Why is
if
that the
the
Can you
case?
repeat the question, please?
The question is that atoms in general have discrete energy levels, that only at certain energies electrons can exist. Okay. Why is that the case? Nitin Kumar is raising hand. Nitin, do you want to say something? Yeah, Nitin, please speak up. Nitin, Aditya, or anybody else,
Sir,
whoever wants to. Yes.
sir, actually, waves, actually, the electrons can move only in those orbits where they can form a standing wave, actually, so their energy is conserved.
Yes, exactly. And that is, I guess, that is also what was being indicated by that the angular momentum can take only h cross value. So this is, first of all, this is because of the wave nature. Uh, but if the electron is not there in the atom, let's say electron is free from the atom, it's in the free space, even then, would the electron have discrete energies?
Yes, sir.
Yes, sir.
Why?
If it is in free space, then what is the energy? The energy comes from the its association with the positive charge, doesn't it?
No, so let's say we can give any energy. So in atoms, we can give any energy to the electrons. Okay, but electrons will absorb only those energies which correspond to the energy difference between two orbitals, two levels. In free space, similarly, we can give any energy to the electrons. First question is, would the electrons exist only in discrete energy states? Second is related to the first one, that would the electrons, would the free space electron absorb any arbitrary energy or only the a fixed amount of energy which corresponds to the discrete energy states? So Deekshant and I guess Devanshu are saying that electrons will have discrete energy states. Om and Aditya, please speak up.
Sir,
I think they have continuous
the
energy levels when
electrons will
they're free. When they're free, they'll have continuous energy.
Sir, I was saying discrete because
sir,
there
I
are
was
infinite orbits. So some way they are linked to some atom also. That's why I said discrete.
Okay, so yeah, yeah.
sir in free state
So
they
some
will
of your,
not have
sorry, yeah, Om, please continue.
sir in free state they will not have discrete energy and they could absorb any amount of energy in free state.
Why do you say so? Reason actually. So whenever you say anything, please also try to understand the reason and explain that. It seems Ayush has raised two hands. So Ayush, you want to say something?
No, sir, it was by
Okay. Yeah, yeah, Om, you were discussing something.
Sir, because in free state they don't have any foundation to be in the particular orbit so that their energy is conserved. That's why they could move in any random direction or movement.
Okay. Uh, Anyone
So,
else?
yes,
So
sir.
the
As somebody said that in atoms, electrons can only move in those orbitals whose circumference is the integral multiple. They should, I mean, they should form standing waves so that they don't lose energy. But when there is no when there is no nucleus around them, they can take any energy because they don't need to form standing wave anymore because there is no there shouldn't be any loss of energy.
Yes, exactly. So yeah, so there are many things here, and one of the most, uh, I guess, interesting or one of the most fundamental conclusion that we make out of quantum mechanics and Schrodinger equation is that, and that comes from the wave nature of electrons, that whenever electron is confined, whenever electron is bound to something, whenever we have a potential which binds electrons or confine electrons, that leads to discretization of energy. So confinement leads to discretization. And there are many explanations for this. One is this standing wave explanation. We can also do maths and solve the Schrodinger equation. There we get the discrete energy levels which are allowed in confinement. So one of the basic principles in quantum mechanics, or one of the uh, I would say consequence of Schrodinger equation, is that confinement leads to discretization. Okay, and that comes from the wave nature of the electrons. In atoms, electrons are confined by the nuclear potential, and uh, as a consequence, there is a discretization of energy levels, and that is because in confinement they need to have standing waves, or they need to have a valid solution of Schrodinger equation, and that is only possible at certain energy values. In free space, there is no such constraint. Electrons can take any energy value, electron can absorb any energy. Okay. In solids, the situation is a bit more complex than the single atom. In solids, we have electrons confined within the boundaries of the solids. So that is one confinement, and second confinement is with the atom. Electrons are confined by the nuclear potential, and electrons are also confined by the boundaries of the solid. So this is a multiple or a two-layer confinement, or two levels of confinement for electrons. And the solid environment is extremely complex environment. There are multiple atoms, multiple nuclei interacting with every electrons, multiple electrons interacting with every electron, electron-electron interaction, electron-nucleus interaction. There might be impurities in the solids as well. There might be vacancies in the solids. So it's a hugely complex environment, and so that's why this energy configuration of electrons in solids is also not so straightforward. It is also quite complex, and that is also the reason, if we do the maths properly, that is also the reason the bands and band gaps are formed in solids, because of this two levels of confinement. Okay, and as we know,
So your
this
screen is not visible.
screen is not visible again. It should now.
Yes, sir.
Is it?
Yes, sir.
Yeah, so it came, it was discovered after the photoelectric effect, because, and as you mentioned, that energy is quantized. So the quanta of energy is very small. That is not, that idea is not relevant here. That idea is relevant in the case of photons, because in photons, energy is directly proportional to the frequency of the photons, and there we have a quanta of energy. Otherwise, a fundamental quanta of energy is very small. Okay, and that point is not relevant for electrons. However, that becomes relevant for electron-photon interaction when we have photons interacting with the electrons. Okay, so second is, in semiconductor materials we have covalent bonding. In covalent bonding, all of you know that electrons are shared by multiple atoms and making molecular orbitals, and electron clouds are there inside the atoms. Just a few facts about the three most important semiconductors. One is the mobility, and second is the intrinsic carriers. Intrinsic carriers mean the number of free electrons inside a semiconductor per unit per cubic centimeter. So at absolutely zero temperature, at T equal to 0 Kelvin, all the electrons are bound to their atomic cores. But when we are operating at the room temperature, some electrons get excited because of the thermal noise, because of thermal energy, and some electrons are free from their atoms and they can move around in the entire solid. And those electrons are actually responsible for the conduction in the solids. So the number of those electrons that are free to move around in the solids is known as the intrinsic carrier concentration. And the carrier concentration, as you can see in three popular solids, is quite different. In silicon, we have intrinsic carrier concentration of around 10 to the power 10 per centimeter cube. In germanium, it is 10 to the power 13. and in gallium arsenide it is very less. That is also one of the drawbacks of gallium arsenide, and that's also the reason that it is used only in limited applications because the conductivity is less. Germanium has the advantage of having quite a lot of intrinsic carriers, but the problem is again with temperature stability. Silicon is in between, and this number of free electrons can also be changed. As all of you know that it can be changed by doping, by putting external atoms into the lattice. The mobility, however, has a different situation. The silicon has the least mobility, which is one of the greatest disadvantage of silicon semiconductors. By mobility, qualitatively, mobility is the ease or is the uh, sort of the tendency to move of for tendency of electrons to move around in the solids, in the semiconductors. So more the mobility, it means that more easily electrons can move around in the solids, which means that electrons can respond quickly to the external electric and external voltages, which means that we can manipulate electrons very quickly. So which means that high frequency applications can be done on the semiconductor, and silicon is bad in that. Gallium arsenide is the best. Germanium is okay, reasonably well actually. So these are very few basic things about semiconductors. We'll talk about doping and some of the devices that preliminary devices made out of the semiconductor materials in the next class, because the time is already over the class time. So do you have any questions about today's discussion or not?
Sir, you said about the band energy capping that arises due to the solid level confinement and the atom level confinement. I didn't get it. Why?
Yes. So maybe I'll share a PDF with you guys. That is not part of this course, but I'll share a PDF where you can read about it, more quantum mechanical treatment of solids and how bands naturally uh, come from quantum mechanics, quantum mechanical uh, solution of solids. And whenever you are back in the campus, we can have, maybe I can explain that to you as well in an extra class or something, okay? That will give a better idea of these things.
Sir, please tell the bondation due to solid.
Sorry, please tell, can you repeat, please?
Sir, you said there were two boundation at two levels, at the atomic level and at solid level.
Yeah, by that I meant that electrons are attracted or electrons are bound by the nucleus. All of us know that nucleus or protons attract electrons. They try to uh, capture the electrons and try to hold the electrons inside that. That is one sort of uh, level of confinement. That is one cause of confinement of electrons. Second is solids have a natural boundary. There is uh, uh, so we have a solid material. For example, there are 10,000 atoms in a solid. After the last atom of the solid, electron needs excess amount. Electron needs a free energy sort of to go out of the solid. So this geometrical boundary of the solid is also kind of a boundary uh, for this for the electrons.
Okay, sir.
Sir, for the
Okay,
project,
yes.
Yeah, sir, for the project, if we take the one where we have to dismantle the a technological a device like a mobile phone and then view all of its components. So, so how detailed do we have to be in that? Do we have to go up to the like individual transistors or just the IC or the main components?
No one can go, or at least we cannot go up to the individual level of transistor, because there are multi-million transistors and we cannot even see transistors with our eyes. So we cannot go to that level.
Yes.
As you will open up the device, you will see many modules, many different ICs. So once you see different ICs, you will know basic structure of the mobile phone or the device, essentially. Okay, and you will know that these are different modules that are there in the mobile phone. Then once you know that, then you need to sort of dig more about those modules, those ICs. What is the basic circuit diagram, maybe? What is the
Okay.
basic functionality? What are and that is not possible just by
That would be
dismantling the device.
theoretical, right?
Yes, that would be done by literature survey from the internet or from the books.
Okay. Okay. Thank you.
Yeah.
Sir,
And also, please don't forget to submit your this video, meet and greet video. Yeah. Any question? There was a
sir, I
question.
talked to some of the
Sir,
seniors.
that
They
big
told about the like for the line follower robot, we need ROS kind of things to work on Python and all. So
You need what? Sorry.
ROS, robotics operating system.
Uh, Not necessarily, as far as I know.
Yes, sir. Like
Although for advanced, you can make it using an Arduino as well, I guess. Arduino
How
or
should we learn?
any other
How
like.
should we learn
So
Arduino?
Yeah, Arduino. First of all, I will put you into next week. I'll put you in touch with the TAs. They will help you out in that. Second is there are many online resources. Maybe we can also share resources with you. So yeah, so this is a free kind of learning. You have to one has to make efforts to learn things, and we will definitely help you out in that.
So how will we learn how to put together all the electronic parts?
There are many resources for that, online resources, even books for that, to learn that. So if you
So
are
can you
not
suggest
aware of
some
the resources,
books?
then yes, yeah. So we can send you web links or maybe books about that. Yeah, definitely. Maybe you guys are not aware of those resources.
sir,
So next week,
Yes, sir.
whenever
sir,
you are in touch with the TAs, you can ask. We will have a WhatsApp group, and you can ask these questions directly to the TAs, and they will maybe immediately and very promptly, actually, they will do this for you.
sir,
Yes.
sir, and about that video, my video is something like 140 MBs, and if the size is 10 MB, so it would be difficult to compress.
140 MB.
Yes, sir.
sir, it must be the mobile
How long is
camera.
it?
That's why.
Yeah. Please reduce the pixel size of the camera. The pixels in the cam, because you might be using high definition or maximum
Yes, sir.
pixels. So we are not
Yes.
mostly we are not much concerned about the video quality. It need not be a 4K video or something like that. It is just an introductory video.
Like I have already made it. Can I just send you on the mail?
Sending on the mail should be the last option. Although I suspect that
Yes, sir.
even emails would support that or not. But just try to compress it. I guess it should be possible. Even a 140 MB video should be possible to.
So
Yes,
the
I
It is
just
easiest
sending
method
on
is to send it to somebody
WhatsApp.
on WhatsApp.
Yes, sir. So
Sorry.
That will compress the video.
it automatically reduces the size of the video.
Yeah, WhatsApp.
Yes, sir.
Yeah. There are these kind of techniques, actually. These kind of simple hacks which you can.
yes, I'll try
You
to
are
do.
right. Yeah, sending on WhatsApp. Yeah. Okay.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you,
Okay.
sir.
Then see you. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.